We can't hear anything.
Over here. The first is this, and the second is this. So that was for the convolutional layer. Now, in the pooling layer, each channel went through a local pooling operation to give you the output of the pooling. So pooling was applied channel-wise. And so when you perform backpropagation, you're going to start off assuming that you know the derivative of the divergence with respect to the elements of this map. And you have to figure out how to take a step back and compute the derivatives for all the elements of the input map. So this is where we were, right? Now let's consider the first case for the convolutional layers. For the convolutional layers, let's first consider how you can go from here to here. Now in all of this, there's one generic principle that we're going to always keep track of, that the loss is a scalar. So anytime I compute the gradient of the loss with respect to any parameter t, I'm putting a transpose here because it's a gradient that I'm speaking of. What will the shape of this gradient be? If I take this gradient of the loss with respect to any parameter p, which could be a vector, a matrix, a tensor, what have you, then what would the shape of this thing be, this gradient?
Same as p?
Same as p, right? Every single element in p is affecting the loss. So you would get a derivative for every single element of p. So this is going to have the same shape as P. So this is a cardinal rule. This cannot be violated. So now, if I have some input of some size, I'll just assume it's two-dimensional, some n cross m, and it goes through some block. I'm not telling you what this block is. It could be anything. And then the output is something else, which is, say, some L cross K. And then from this, there are further operations, and then finally you compute the loss. What would the size of the gradient of the loss with respect to this thing be? L cross K. And that one? N cross M, right? The size has to be recovered. Even if this is smaller than this one, when you pass the derivatives backwards, this derivative must be the same size as the input to this process. So this is the idea that we're going to be using, right? We'll verify the sizes. So in the first step, we're going to backpropagate the derivatives from here to here. Now these are pointwise applications of an activation. So if I have some y out here, which is some function of some z out here, if I have dl over dy, where L is the loss, then I can say dl over dz equals dl over dy times f prime of z. This is your standard chain rule, right? And so that's what we would apply out here. For every single element in the activation maps, we'd pass the derivative backwards to the affine maps by simply multiplying it by the derivative of the activation function itself computed at that particular value of z. Right? So this is, again, all from the previous class. Nothing new over here. So we know how to perform this first step, this guy. Let's see how we do the second step. Again, we explained this in great detail, but here's what happened. You had a collection of input channels or input maps, right? And then you had several filters. Each filter in turn had several channels, as many channels as input channels. So in order to now, where's my pointer? So in order to compute the derivatives for any input channel here, you would have to consider all of the output channels, and each output channel is going to interact with this guy through the corresponding channel of the filter which generated this output, right? So you're going to pull out, to compute the derivatives of the mth input channel, you're going to pull out the mth channel of all of the filters. And so that's going to, you can think of them as your new filter. Then each one of these is going to be, each channel of filter channel is going to be flipped left to right, top to bottom. So you're basically transposing the entire operation. If you think of the entire block of filters as a giant tensor, you're transposing the entire filter. That's one way to think about it, right? And now you would convolve the map of derivatives of the output with the filter, with the transposed, which is, you pulled out the mth channel, then flipped left to right and top to bottom, and then you convolve the output derivative map with it to get the derivatives for the input. Now, we said we had to zero pad. Why did we have to zero pad? Let's take a look at this size rule again, right? When I'm performing my forward convolution, if I have an input of, say, size m out here, if the width is m, and if I convolve it with a filter of size k, and let's say the output is size n. So this is y, this is my filter, and this is my output z. What is the relationship between m, k, and n? Anybody remember? What is the relationship?
N is equal to n minus k minus 1.
What was it again?
N equal to
N minus?
k minus 1.
So n was going to be your m minus k minus 1. Is that correct? Are you sure?
Plus 1.
Plus 1, right? This is this way. You're going to lose the width of the filter -1 columns, correct? So now, if I directly convolve z with k, what would the output size be? So let's say this is the map of derivatives, not z itself, but the map of derivatives. But the size is still going to be n on one side. If I convolved it with the filter, what is the output size going to be?
K minus 1.
So this is going to be that output would be n minus k minus 1, which is going to be m minus k minus 1 minus k minus 1, correct? Because this is what happened, this was what n was. So in other words, m minus 2 times k minus 1, correct? Which is why you had to pad it with 2 times k minus 1 zeros. K minus 1 to the right and k minus 1 to the left, to make sure that the derivatives that you got for the input were the correct size. That makes sense to everybody? Right, yeah. So, but the operation, of course, was easy. You zero padded the z derivative maps and then transpose the filter. Basically, you pull the mth channel of all the filters, flip them, and then convolve the collection of zero padded derivative maps at the input, and then and that gave you the derivatives for one channel of the input. But this could be repeated many times. We also saw how to compute the filter derivatives. Now, the derivative of the loss with respect to any particular filter channel has to consider only one term. So over here, if you look at how, say, the nth output channel relates to the mth input channel, that's computed using the mth channel of the nth filter. So any single channel of any single filter only relates one output channel to one input channel, right? And so what we found was to compute the derivative. There's no transposition anymore over here. To compute the derivative for all of the elements of the filter, all you had to do was to compute the input channel, convolve the input channel directly with the map of affine derivatives. And then once again, you can verify that the size is going to be right. How so? So going back here, if we were convolving this with this guy, correct? But we have n equals m plus minus k minus 1. Now, if I convolve this term with this term, what is the result going to be? What is the size of the result? Anyone? Yeah.
Minus n minus.
It's going to be n minus m minus 1. But then n was again m minus k minus 1, right? So minus m minus 1. Is that the correct answer? Right? You're going to get a sign flip. These will cancel out. These will cancel out. There's a minus k, but the size is going to be right, right? If I wrote it the other way around, you'd get the correct answer. But what you find is that if you convolve the input with the derivative maps directly, the result is going to be exactly the size of the filter. Denise, you're looking lost.
I'm just, I guess, was lost over why the size was negative k.
Because I wrote it wrong, right? If I were to write this as if I were to write this as m minus n minus 1, right?
And that's the size that we get from
This is the n is the size of z, m is the size of the input.
Yeah.
Correct?
Yeah.
So this is going to be m minus, and n is going to be m minus k minus 1. Correct?
Yes.
Minus 1. So these will cancel out.
Okay.
The minus and minus become plus, and these cancel out, right?
Plus k.
Yeah. I was just being careless. But you'd see how the sizes work out. Okay? Any questions? So we figured out how to go through the compute the derivatives for the convolution layer. Any questions? This was just a quick recap. All right. So for pooling layers, how did we compute the derivative with respect to the input layer? So here again, we saw that pooling basically just goes through top left to bottom right. If you're performing max pooling, within each block, you're picking up, identifying the location of the maximum and copying that over, right? So when you go backwards, you're assuming that this, say to compute this top left element, let's say you looked at this window of inputs, you'd pick the largest. The largest would be maybe the 6, right? So if you went backwards, this was the only element that influenced that output. So the derivative over here is just going to get copied back into this location. That was the simple logic that we applied, right? And so literally, if you wanted to write the derivatives backwards, all you would have to say is that the derivative, it's easier shown in code. This is what the pooling, max pooling looked like going forward. At each location, you found the location of the, within each window, you found the location of the maximum and read it out, right? Going backwards, it's much simpler. You only increment the derivative at the location of the maximum. The rest do not matter, right? So, and then for mean pooling, we saw the same thing. In mean pooling, the output is the average of all of the elements in the window. So when you go backwards, the element over here gets equally distributed over the entire window. It's just uniformly spread out. And so code-wise too, that's what it looked like. This was the forward mean pooling. Within each window, you just computed the mean. Going backwards, everyone at every location within the window, you just incremented the derivative by 1 over k squared times the derivative at the output. But then observe something. Mean pooling is convolution, is it not? What are you convolving with?
Kernel that sums to 1.
A kernel where all the values are equal.
Yeah.
1 over k squared. And so you can really think of, so you can use the same trick as before, right? You can pad your inputs, pad your z derivatives with zeros all around, and just do this channel-wise. Just perform a convolution channel-wise and with a uniform kernel, and you're going to get the same result. And so we know how to deal with convolutional layers and pooling layers. Your first poll, guys. Can someone time it? Okay, 5 seconds, guys. Okay, you're out of time. What is the answer for the first one? True. And the second? Perfect, right? We got both. So far, so good. But then many of you asked me this question in the last class. How do these rules change when we have a stride? I said, I'm not going to deal with strides, right? I promise you that you won't be dealing with strides either. Instead, we're going to consider the 2 other kinds of operations that we haven't seen. We haven't actually explicitly considered the backpropagation rules for upsampling and downsampling. Upsampling increases the size of the map by introducing zeros. Downsampling throws away elements, and so decreases the size of the maps. And upsampling followed by a convolution can be viewed as convolution with a fractional stride. And convolution or pooling followed by downsampling can be viewed as convolution with a stride. We saw this, right? So here's what the downsampling layer looked like. When you were downsampling, you had a bunch of inputs, and throwing away values is the equivalent of saying, I'm just going to set them to 0, right? So you set s minus 1 of every s columns and s minus 1 of every s rows to 0. So the first step was to go from this element here out to this element here, right? and then you just compacted the whole lot. So now there are two steps over here, right? Now consider this guy. This guy's value, what is it effectively? The black location, 0. Does perturbing this change that value? No, right? So that means the derivative of this entry with respect to this guy, what is it going to be? 0. I can ignore those elements, right? So the only elements that really are going to be passing non-zero derivatives backwards are the colored ones. The rest of them are forcibly set to 0. They are not going to affect the output, right? And so if I want to compute the derivative going backwards, remember again that the derivative must have the same size as the input, right? So the first thing I would do is maybe allocate a map of derivatives of the correct size. And then while coming backward, I would expect that I already have the derivatives for all the elements of the output of the downsampling. I know these were the only locations that got copied forward during downsampling. So all I need to do is to set the rest of the derivatives to 0 because we know that they do not affect the output, right? And these elements are going to get copied over, location by location. So because any perturbation over here is going to directly reflect as an exactly equal perturbation on the downsampled image, right? And so for each location in the downsampled image, you know where it came from in the original image, and you can just copy the derivatives over. And for the rest of them, the derivatives are going to be 0. So backpropagating through a downsampling layer is a trivial operation. That making sense to everybody? Any confusions here? Right. And so downsampling is easy. And here's some pseudocode. Basically, you allocate some zeros and you just copy stuff over, right? The other was upsampling. Now, in upsampling, you introduced zeros between rows and columns, right? Is there anything out here that will cause a perturbation of this element? No. So this really has no derivatives going back here, right? And so when I'm backpropagating through an upsampling layer, when I've computed my derivatives coming all the way here, I'm going to have a derivative for every element in this map. But then I'm only going to retain the ones that actually were propagated forward during upsampling, right? And those would be copied backwards. So again, this is a trivial operation. Questions? No. So yeah.
Aren't you like losing a lot of information?
So that's you're not losing information. You introduce zeros, right? All you're saying is that if the 0 were not 0 but epsilon, I'd get something else. But that information has nothing about that. Is just externally forced and has nothing to do with the actual input itself, right? So everybody with me so far? And so this is why, so this is what the pseudocode, that's the backpropagation through upsampling. Now, what does this look like? Backpropagating through an upsampling layer looks like downsampling, and backpropagating through a downsampling layer looks like upsampling. You have to do some adjustment of indices. It's not exact, right? Because there's some boundary effects that you'd have to worry about, but conceptually, they are the mirror images of one another, right? So now, if I'm convolving with a stride of 2, what exactly am I doing? I'm convolving with a stride of 1 and then downsampling by 2. Do I have to worry about how do I perform backpropagation through a convolution that has a stride of 2?
No.
I just backpropagate through the downsampling layer, which is a very trivial operation. And then I just do a regular backpropagation from there, right? Yeah.
But won't this like waste some computation power? Like, because we will basically just throw away 3/3 or 4/3 of our computation results.
Indeed, it would. If you want to be very efficient, then you can figure out which ones are actually being computed. But conceptually, Which would you rather implement? Right, that's my question to you. So do you want to work out the indices, figure out how things are added, or just do this? So easy. You can just backpropagate through the downsampling and then backpropagate through the convolution layer. What about upsampling? You know, convolution with a fractional stride. Convolution with a fractional stride was upsampling followed by a regular convolution, right? So if you want to backpropagate, what would you do? Just convolve through the through the regular, backpropagate through the regular convolution, and then downsample, right? Or you could do something more fancy. Which would you rather do? So easy. So this is what you do. Pooling and downsampling. Again, when you're pooling, you typically take a stride, right? But what are you actually doing? You're pooling with a stride of 1 and downsampling. It's kind of convenient to also think of it along those same terms. So regardless of whether you're pooling with mean pooling or max pooling or what have you, it's always conceptually much simpler to decompose things into simpler things for which the operations are trivial. Or you can be masochistic and work out the math. I encourage you to do the latter because I like you to waste your time. But no, I don't. But anyway, but then here's an even simpler way of looking at life. You write code, right? And so at the end of the day, when you're backpropagating, what are we really doing? We are starting at the last operation and then working our way backwards through the derivatives, right? So here, I'm just going to use one very simple rule, or a couple of simple rules. And it turns out this is all that you really need to remember for these things. Suppose I have, z equals x times w, all scalars. Then if I'm given dl over dz, then what is dl over dx? This is going to be w times dl over dz, right? What is dl over dw? This is scalars, I said, right? X times dl over dz. So this is a very easy thing. You don't have to think about things very hard, right? It turns out you can use this. And the fact that you are backpropagating. So here's what your forward propagation is going to look like if you're writing code. You'd be within each layer. You're scanning the input, right? Then at each input for each filter. So when you're scanning the input, you have several input channels. At each filter, you're going to start at some location. So you'd go through these input channels, right? And then within each input channel, you're going to scan over the region of the filter. And then at each location, what are you really doing? You're just multiplying the filter weight at that location with the y value at that location, and adding that product to z. When this is completely performed, at the end of it all, you apply an activation. This is the forward code. We wrote loads, we've gone through like 11 lectures to give you this trivial operation that you're going to multiply two numbers and then put it through a nonlinearity, right? Add them up and put it through a nonlinearity. But then once you realize this is all you're doing, forget about all the fancy theory, then I can flip things. So when I'm working backwards, here's what I will do. I will reverse the operations. So look at how the indices are going. I'm going to unwind. If I'm winding forwards, I'm going to unwind. Look at the indices. They're going from 1 through W, 1 through H, 1 through D, 1 through DR minus 1, 1 through K, right? I'm going to rewrite it, and every index is going to go from the largest value down to the smallest value, right? So this is performing the operations in reverse, right? Then the last operation I performed over here, after going through this loop, was the application of the activation, right? So just before going through that loop, I'm going to be doing this one. The other rule that we will use is if I have y equals f of z, dl over dz equals what? dl over dy times f prime of z. There's the other rule that we are familiar with, right? And so what was being done at the bottom out here is going to be done just before this loop, because it was after the closure of that loop that this operation was performed. And all I am doing is saying dl, this is the derivative of the loss with respect to z, is the derivative of the loss with respect to y times f prime, right? So I changed that. And then within the innermost loop, I just use this rule. That's all I did. At this point, when I come here, I've already got the derivative of the loss with respect to z, because that's what I computed out here, right? And so I can just say dl over dy plus equals w times dl over dz, and dl over dw equals y times dl over dz, right? That's basically just the application of this little rule. I changed my code. I changed the indices, and I changed 3 lines of code. This will do my backprop for me just fine. I didn't need to do anything else. This making sense to everybody? Yeah.
So does that domain handle, like the change of indices, does that handle the flipping of the
This is the math operation. You don't have to worry about, any of the additional concepts, right? You're literally saying z equals w times y. So dl over dw equals dl over dz times w, and so on, right? Everything should be correct. Now here's the beauty of it. If I were doing this with a stride, I'm going to do the same thing. All I'm doing is flipping the indices, and the loops are now going to stride. Nothing else changes, and the math should just work, right? So when you look at it through code, it's so much simpler. Make sense to everybody? And same thing with pooling, right? Well, pooling's easy. I'll skip this, right? Instead, I'll give you a poll. Okay, time's up, guys. Someone on Zoom, answer all 3. Is the first statement true? Yes. On Zoom?
True.
Second one.
True.
Third. And the third.
False.
False.
Perfect. And why is the third one false? Yeah. So, all right. So now we know how to compute the derivatives for all of these guys, right? No more confusions. Now we know how to do the entire operation, beginning to end. So the story so far, the convolutional neural network is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, and downsampling layers, which are, basically pooling layers are called downsampling layers because pooling is usually performed with a stride, that operate over groups of outputs from the convolutional layer to reduce not the network size. I should fix the slide. Somebody posted on. Yeah.
Right. On the poll for the last question, is the reason why we cannot use upsampling layer as the backward positive downsampling and vice versa because of the weird index stuff that we have?
Yeah, we'd have to worry about what's happening at the boundaries.
Okay, because it's not perfectly upsampling or perfectly.
Yeah, it depends on, so when you're upsampling, for instance, you're not going to be introducing zeros beyond the boundary.
Yes.
When you're downsampling, you'd be throwing things away if you.
But if that is true, why are the first 2 questions true?
So they look very much like downsampling, right?
Yeah.
It is, but you can't just, the operation you're performing is upsampling.
But you cannot say it's an upsampling layer, right?
You cannot use it as an upsampling layer, right? So think about this case where I have 8 inputs,
Yeah.
okay, and I'm downsampling by 3.
Yeah.
I'm going to take the first output and the 4th output and the 7th output, right? The 8th is gone.
Yes.
I'm not going to be, I don't know how many I lost going forward at that point. Whether I had 8 or 9, the output is going to be the same size.
Oh, okay.
Right? So you'd have to be very careful about that.
Okay, so it's not perfectly an upsampling or downsampling.
Because you're losing information at the boundaries. Yes.
For the backpropagation of the upsampling case, I only consider the interpolated zeros as inputs with zero.
Meaning?
Like, why do we discharge the derivatives?
So where do you pass them back to?
But if we consider the interpolated zeros as inputs.
Yeah, inputs, that's going to be going in at that location. There's nothing going further back, right?
No, but in the next,
The derivatives are going to come all the way to that layer, but there's no way for them to go going backwards. There's nothing further earlier in the layer that's going to influence those values unless you use some other formula rather than 0 to insert them, right? Okay, so now the parameters of the network can be learned through regular backpropagation. The summaries on the slides, right? But then there were a few more questions asked. How do you handle scale? If I'm looking for flowers of this size, what would I do if my flowers were larger than that? If I'm looking for flowers, if my network has been learned to recognize flower, when we trained CNNs, the idea was that the network must fire regardless of whether the flower occurred here or here. But would that network fire if the flower were like this? Would it? No, this is not a flower. This is an upside down flower, right? What about for this guy? What about for that? They don't look like the pattern that you're searching for, right? It has shift invariance, but it doesn't have scale invariance. It doesn't have rotation invariance. It doesn't have reflection invariance. The only way you're going to be able to introduce all of these invariances is by providing those also as training examples, right? So that it knows that an upright flower and an upside down flower are the same thing. But what if you don't want to do that? Yes, Etienne?
Yeah, so like why can't like the CNN have scale invariance? Because we have all the pooling. Like for example, if we have max pooling, then for example the y is 2, then either like they have maybe like activation value of 10 with 2 by 2 or
It doesn't matter, right? What is the CNN actually doing eventually?
extracting features.
No, it's scanning for a pattern, right? Whatever pattern you're scanning for is what you're going to be looking for. That's it. If you want to have different sizes of patterns to be detected by the same scanner, then they must be part of your training data. You have no choice. It doesn't automatically learn to handle size variations, right? So if I want to, but suppose I only want to give it pictures of upright flowers, and yet I wanted to be able to find flowers which are at 45 degrees. What can I do? I don't have those in the training data, yeah. That was very muffled. I'm sure it was a good answer. It was very muffled. Yeah. Yes. So can you repeat that?
Transform during inference and then get the highest.
It wasn't clear. I'm so sorry. Yeah.
It's rotated. Can we just do like diagonal scans across the inputs?
But the pattern itself is not rotated, right? So here is what we would have to do. Think about what your standard shift invariance is doing. Your shift invariance is looking for a pattern, right? And at each location, it's going to be looking for the same pattern. If I also wanted to be able to look at a rotated version of that pattern, I must rotate the pattern, right? And so I'd say these two are the same pattern, but one of them is a 45 degrees rotated version of that pattern. And so now from the single filter that you had, you would create the original filter, which is looking straight up for that pattern. And then you'd have something that's a rotated version of that filter. And the rotated version of the filter is going to look for the rotated pattern. And so more generally, you can have a whole collection of such transforms, right? I want to say, I want the original pattern. I want to detect flowers which are upside down. I want to detect flowers which are bigger. I want to detect flowers which are at 45 degrees. Each of these is an independent transform. I want to detect flowers which are slightly bigger and at 30 degrees. That's a transform all by itself. And so for every one of these transforms, you would have to create a transformed version of the filter, the pattern that you're actually scanning for, and then use those on your collection of input channels. And so each filter and every one of its transformed versions is going to create an output channel. Yes.
Professor, would this mean that, like, in terms of the complexity of features that we give to our network, like we have a complicated network to begin with. Now we're adding all of these like rotations and everything, and it's becoming exponentially more complex. So I was just curious whether we would do this during training, or we would do this after we do the model, we train it on normal images, and then during training.
So you want to do this both at training and at inference, so that it learns the features which are invariant to these specific transforms that you have given. You wouldn't actually do it, but yeah.
Are these different networks and you're taking a max of all the...
No. So I'm just saying that, if I'm looking for a flower or if I'm looking for a petal, I'm going to be looking for the petal, but then I'm also going to rotate the petal a little bit and then scan for the rotated petal. I'm going to reflect it. I'm going to scan for the reflected petal, and so on. And each of them is an independent one, yeah.
Oh, so they're going to be trained independently, right? All the weights are going to be trained independently.
So no, here's the bet, right? So wait, let me answer that question, yeah.
No, I just have a question of like, won't this only then like constrain your model to like specific transform?
Thank you, yes, right. So here you go. So this was your standard CNN, right? At each position, you pulled out a segment, and then you convolved it to the filter. If you want to introduce this kind of transform invariance, which is why you never see it in a real CNN. This is conceptually, meaningful, but practically it's horrible. Why would you want to do it? You just throw in more training data. But for completeness sake, you must know that this is what you would have to do. At each position, after having pulled out the segment for each filter, you're going to make many copies of the filter, one for each of the transforms that you're permitting. And then you're going to scan with every one of the transformed versions, which means that Sharan is right. Only the transforms that you've explicitly listed are going to be a part of your invariance. Any other transform is not going to be accounted for. So when you're backpropagating, you'd get derivatives. Every one of the transformed versions of the filters would generate an output channel, right? So you're going to get derivatives for every one of these output channels. And then you'd have to pass those derivatives back through the inverse of the transform, so that you know where in the original pattern they're going to combine, and then aggregate the lot. Yeah.
So won't this fail at the edges? If I rotate my filter and try to scan them at the edges, if there are features that we have to recognize that fail.
Zero pattern. I mean, all the problems that you have with regular patterns would occur over here. This is not going to introduce anything new, right? Yeah.
And also in backprop, if we, let's say if I'm looking for scale invariance, I try to increase the size of my filter. How do I add different shapes?
Meaning? No, so the transform. So here is what you would do. This is this. So this is like, if I'm scaling, this is like taking my filter F, and then I'm putting it through an upsampling layer, right? With interpolation, maybe not just introducing zeros. And then I'm getting F prime. So now when I'm going back, I'd have derivatives for F prime. I'd have to put it back through this guy and then aggregate the derivatives. Yeah, there was another question.
So assume we do this transform the way we do it. And my question is that assume you train it on a certain data, and the test data is only different in terms of it contains the listed transform invariances, but everything else is the same as the training data. In that case, will it be impossible to overfit on the training data, given that we take care of these transforms as well?
Overfitting is a different can of worms, right? It also depends on the size of your training data and a whole lot of other issues.
Right.
So the question is kind of
Like,
hard to answer.
will it recognize these listed invariances if all the other attributes or features of the data?
So the point is, if your training data only has these transforms, then you're going to be able to account for them. Whether it overfits to your training data, I mean, if your test data only has these transforms, you're going to be able to account for them. But whether you will overfit to the training data or not depends on the size of the network, how much training data you provide, and other factors, right? There was another question.
Like technically, isn't this the same as augmenting your training data and increasing the size of your network?
Not really, right? Because you're constraining it. You're saying that these are all the same variants of the same pattern. So where there you'd be learning independent features for the various variants, right? Yeah.
Like just going on that, like practically it would make more sense to augment the data, right? Like rather than, because we would still have like cases where we
Practically, you wouldn't actually do this because computations are horrible. Back propagating the derivatives through the transforms is really hard.
Can we understand it as like in this way, like instead of augmenting data by this like training multiple like with multiple transform weights, we are enforcing all the weights to be updated at the same like with same gradients, which might be more accurate compared to augmenting data directly.
So the problem is this: the implementation wise, this is going to be much more challenging. It's much easier to just rotate your input than to begin dealing with various transforms of your filters and then figuring out how to back propagate derivatives through the transformation of the filter. Yeah.
Professor, is it the same filter?
Yeah. So one for each filter is going to become many variants, right?
Right. So like we have, let's say, just 20 filters, and let's say I have 10 transformations.
Then you're going to have 200 effective filters, but only 20 basic filters.
But I basically update only 20 filters, right? What
Yes.
I'm going to do is
You're going to get derivatives for 200 filters,
Yeah.
which are going to be aggregated into 20.
I'm going to take the inverse and then aggregate it
Yeah.
back to the original.
Yeah.
Okay, that makes sense.
Yeah, Josh?
Thank you.
And does this also blow up over layers? Like, do we perform this rotation or?
It would be up to you, but in principle, you'll be doing it everywhere, right? So it's going to get horrible. Or you could do it at one layer. But the point is, nobody really does this. It's just easier to augment your training data and not worry about it. Yeah.
I get the rotation case. The transformation of the filter would be also to rotate the filter. But to achieve scale invariance instead, what kind of transformation?
You'd scale the pattern, right? It's just a pattern. You can just update. You can start with an image and have some kind of linear scaling of the patterns in the filter itself. It's like an image. You can always upsample the image, right?
Oh, okay.
Yeah. Anyway, let's continue because this is only a concept. Nobody really does it. So adding this, the parameters of the network we saw can be trained through regular backpropagation. And the models can also be easily modified to include invariants to other transforms, although these tend to be computationally horrible. And so it's not a recommended strategy. Right? There's more to it. All of this is only saying, tell me if the image has a flower. It doesn't tell me, I say, where in the image is the flower? Suppose I also want to find the location of the flower. Is that information here? It is, right? Because you're scanning each location and you're finding, and the result is saying, is any of them a max? Is the max of these a 1, right? Is any of them a 1? If any of them is a 1, you can find out which of them was the 1, and you can find the region where the basic pattern occurred. Now, you wouldn't do something that crude, but the fact is that information is there once you learn it. And so you can use that information to actually draw bounding boxes for objects. And so a standard technique is to take the output of the final layer, which goes downstream to your classifier on the one side to tell you if there's a flower or not. But then it goes also simultaneously into a second prediction layer, which uses these features to predict the corners of your bounding boxes, the coordinates of the corners of your bounding boxes. And now when you train the network, the network is going to have 2 losses. One is a loss from the classification layer on top. That would be a standard Kullback-Leibler divergence. Then the lower layer, which predicts the corners of the bounding boxes, can use either L2 losses between the correct and predicted corners, or you can look at an intersection over union loss to see if the bounding box is indeed enclosing the flower. And this loss can then be backpropagated. So the final loss is going to be a weighted sum of two losses, and these would be simultaneously backpropagated. Now the same technique can also now be used to predict the joints of a stick model. I don't know, you folks haven't been here very long, but if you were here before COVID, every time you walk from the Hillman building to Newell Simon Hall, you'd walk down this long corridor. And at the end, there's a giant screen where Yasser Sheikh had a demo, where it would actually draw your skeleton as you walked in. If there were 8 of you walking in, there'd be 8 skeletons on the screen. It was scary because it was that accurate. It would get every one of your joints and actually draw a skeleton walking by. So now, for that, you need to find the locations of these joints, right? You can use the same technique. So here's a poem. Okay, time's up, guys. Yes.
So for the pose estimator and even the flower example, like isn't the CNN in theory just like looking at bigger and bigger boxes as it goes down the limit?
Correct. Eventually, it's telling you something about the very input, right?
Right. So then, don't you like lose that information of like where exactly it is? Like, won't it be better to take information from like a previous?
We discussed something about losing information earlier, right? What was it we said? If the actual number of variables you finally computed equals the number of inputs, then information need not be lost, right? So long as you make sure that you have sufficient information at the end, all the requisite information must be there. Yeah.
Building on that, what if you have multiple boxes that have the same thing, like in the same layer if you have very similar?
Yeah, that's where you get into fancy things like RCNNs and so on, where they do a region proposal, and within each region they run this the same algorithm. So it gets more complex. But the idea is you actually look at it in regions, in little blocks, and then make predictions within each box. And then you have some additional heuristics to aggregate the lot. So ULO and RCNN, yeah.
This might be a more basic question, but you mentioned that you just do data augmentations for like different angles, but you can have infinite angles, right?
So if the entire hypothesis is that if you do enough, then if I give you 5, 10, and 15 degrees, the hope is that you cover the things in between as well.
So if I do 5, 10, it would be able to detect 7.5.
Or detect a 7.5 rotation of the pattern. That is the hope. There's no guarantee, right? Yeah. Yeah.
In the bounding box loss, do we enforce constraints for x1 to be less than x2 or so on?
If you use an intersection over union, then that would sort of fall in, right? You could, again, yes, yeah.
For bounding box problem, do we actually find the data with actually labeled?
That they would have to be labeled. Your training data would have to be labeled.
Do we actually get that? Because it's easier to find 100 images with flower and not flower, but actually all coordinates.
There are data of that kind, right? I mean, there's some work on doing this unsupervised, but almost all of the systems that work well have labeled data. Yamuna?
Yeah, for the pose estimation one, since the skeleton of the person that's drawn is like the middle of like each one of like the head and like the stomach and stuff, why don't we do something like that, like for example, like for flowers? Like
it's not in the middle. These things are actually I mean, my shoulder is not in the middle of my torso, right?
Yeah, not the middle, but like relative to like to the ideal skeleton. Like
so those have been learned from some training data that have been manually tagged. And so if you had something similar for the flowers, yeah, that's basically what Yash was also asking, right? If you had label data of that kind, yes, you could learn those things too. You'd need to label the kinds of predictions, geometric predictions you'd want to make. Yes, you can.
I have a question regarding the scaling invariance. Like in traditional computer vision algorithm, there is something called like image pair pyramid where we basically like scale, given an image, we create a pyramid of image with different scale, and can we do similar thing?
You definitely could, right? So again, you could be analyzing the image at different scales and try to find stuff. The training algorithms become more painful. How do you incorporate the scale image, image pyramid in training? Yeah.
So in a CNN, is it generally better for the filter size to be bigger than the object you're trying to find?
No, you want a lot of small, because you're cascading these things over many layers. Remember, you're distributing the representation, right? So each filter can be very small. You really want them to look at the smallest patterns you can capture.
If the filter is smaller than the image that you're trying to identify, then
the aggregate of the filters over many layers. Remember, you're distributing the pattern. If you go back to the examples from several classes ago, I had many filters which are looking at 2 time steps, but the actual MLP that was scanning the input was looking at 8.
But can it be possible that the image is not continuous? So say I break down the flower into like 8 small pieces and put it on all across the image, because the filter is still smaller than the actual image size, then will it still be able to identify this as a flower, but
Would you?
It's not?
If you can't do it, don't expect the poor CNN to do it, right? Yeah.
Is it possible to like add a MLP before CNN to account for the transform?
You could try. I haven't heard of it. Transforms are a painful thing, right? There are different kinds of operations. So I'm not familiar with anything of that kind, but one could, I mean, things like rotations and such like are basically linear operations, right? So, yeah. Anyway, let me continue, guys. Yes, one last question, Rana.
Is it possible to make it invariant to partial or overlapping patterns?
Partial or overlapping patterns. That's no different from your standard training, right? So it's not part of the CNN framework itself. That's where, for example, dropout makes it robust to detecting partially occluded patterns. And here are the answers, because we spent so much time on the discussion. They're all true, so it was easy. Now, there are many other kinds of variations. Things like very deep networks. If I have 100 or more layers in an MLP or a convolutional network, you will see in a couple of classes why training such networks becomes problematic. We saw earlier that given a number of parameters, fixed number of parameters, you're better off arranging them in terms of depth rather than in terms of width when it comes to getting nice, smooth representations. And we saw some examples of how that worked. That's the concept of it. But then the training becomes a pain, because when you compute your backpropagate derivatives through the slot, then you find that it's very hard to get derivatives to actually update your parameters. We'll discuss this in a later class. And you also have this issue of too many parameters. How big does your model get? And how can you run things on small devices and so on? So you have this alternative variant of convolutions called depth-wise convolutions. And let's take a look at what depth-wise convolutions are, because these are very frequently used. Now, suppose I have a bunch of input channels, say 10 input channels. How many channels will my filter have? Each filter is going to also have 10 channels, right? What is the actual operation being performed? Each channel of the filter convolves the corresponding channel of the input. So if I have 10 input channels, I'm going to have 10 channels of the filter, each performing its own convolution, generating its own map, and then all of them are just added up into a single map, right? And that's going to be the output map or the output channel for the filter. So if you have many filters, 3 filters in my example, and let's say I have 10 input channels, in effect, you're computing 10 convolutions per filter, right? Because every channel of the filter is convolving the corresponding channel of the input. So you're computing 10 convolutions per filter. You'd have 3 filters, you have 30 convolutions. And these are going to give you 3 output channels. There's a different way of distributing this computation. And that's what depth-wise convolutions does. This is like mean pooling. Remember, mean pooling was just operating channel-wise. So imagine that instead of performing mean pooling channel-wise, you had a pooling operation which was learned. So you're going to have a different filter for every, you're going to have a, you're going to have a different mean pooling like filter for every channel. And each channel is going to get convolved with just its local, that corresponding plane or that current corresponding filter channel, right? And now instead of just collapsing the lot into a single output, you can collapse them using different weights. So here, instead of doing what we did here, where each channel of the filter produced its own output map, and then you just added them all up. Each channel of the filter will now compute its own output map, but you won't just simply add them up. You're going to add them up with different weights. And by changing the weights, you can get different outputs. And so now if I do this, this is still giving me the same number of output channels as before, but the total number of parameters and the total number of computations is going to be much smaller. Of course, this is also a less powerful model, right? This is what is called depth-wise convolution. So to compare, that's your standard convolution. If I had m input channels, and if I had n output channels, so if I had n output channels, how many filters would I have? N also, right? And let's say each filter was k cross k. So then each filter is going to have m times k cross k parameters, right? And so, and if I have n of these, I'm going to have n times m times k squared parameters in all. If I do this depth-wise instead, I have one set of k cross k parameters, right? It's m times k cross k. That's mk squared. And then after they're formed, I'm going to be collapsing these m channels into n different outputs. So I need m times n weights. And so the total number of parameters is nmk squared versus mk squared plus n times n. That's going to be orders of magnitude smaller. Yeah.
Just a quick question about depth-wise convolution. How are you doing that second step where you're combining after you convolve all the filters?
So suppose I have a filter with say 10 channels, right? So I'm going to get 10 output maps, correct? Then in one case I could do, 0.1 times first map plus 0.2 times second map plus 0.3 times the third map.
Okay.
In the other case I could do 0.3 times the first map times 0.2 times the second map times 0.1 times the third map. It's going to be a completely different combination.
You're not directly taking your output, you're scaling it by some given weight and then
And those weights are learned. That's like having a non-distributed scan, right? That's your 1x1 filter, 1x1 convolution.
But in both cases, you would end up with the same amount of output channels.
You're going to end up with the same number of output channels, right? Just that the number of parameters are far fewer, and the number of computations is also much fewer, because the number of convolutions you have to perform goes down by a factor of n. And so if you're implementing things on small devices, this is a method of choice, yeah.
Professor, is there something in between where we have m independent k by k to e filters, but they act on all input channels and not just only one?
I'm not sure I understand what you're saying.
Okay, maybe it's a weird question, but like
it's not a weird question. It's just that I don't get it.
In this instance, for every channel, like each filter only applies to only one single input channel.
Okay, you're suggesting what if you have each filter applying to more than one channel?
Yes, but it would be two-dimensional. It wouldn't be specialized for different channels. It would be one filter applying to all channels.
You name it, and every combination of it has been proposed. Combination has been proposed. These are the two extremes. So what you suggest is probably a paper out there, some minor paper out there, because so many variants have been proposed. Because it makes sense. Once you see the two extremes, you can think of all of these other variants in between, right? And so people have tried. It's a trade-off between compute and parameters and accuracy, yes.
And this is a difference between compute and accuracy, right?
Is there like any strict relation between like n and m? Is it
M is the number of input channels, n is the number of output channels. That's about it, right?
Is it like guaranteed that it has to be equal or greater?
No, we didn't. Remember, this is just a standard convolutional network. The number of output channels depends on the number of filters, right? We said there was no real relationship between the two. And what the number of output channels times the size of the individual maps, you wanted that to be more or less at least as many as the total number of parameters in the original input if you wanted to retain all information. If you were willing to lose information, that could be smaller, but that's about it. There are no hard and fast rules over here. Let me continue. So, that's it. 10 seconds, guys. 2 easy ones. Okay, time's up. Who wants to answer the first one? Yes. And the second? Yep. Thank you. So apparently I've been conveying the message. I'm happy to take that. And so to extend our story, convolutional networks can also make predictions. The last 2 bullets, these are the new things that we've learned in the past 10 minutes. They can also make predictions related to the position and arrangement of the target object through multitask learning. It's multitask learning because you were learning 2 tasks at the same time. You were learning to classify and you were learning to detect the bounding boxes. So there were 2 different tasks you were performing. So this kind of learning is called multitask learning. And several variations of the basic model exist to obtain greater parameter efficiency, better ability to compute derivatives, and so on. Okay. So, but what do the filters themselves learn? Remember, we are scanning for patterns at hierarchically, right? Each filter learns to detect a specific pattern. Now, in the input layer, it's very easy to know what, in the first hidden layer, it's very easy to know what the patterns are because you just look at the pattern of weights for the filter. But when you get to the next layer, it's impossible because it's different combinations of inputs could make those second layer neurons fire. So the way you would have to do it is you would actually have to figure out what it was about any specific input that generated a specific output in the second layer filters. And you would do it by perturbing the input. If perturbed the output a lot, then that was relevant. If not, it was not. So you'd have to actually use backpropagation to compute these, the receptive field. So the receptive field of a filter is the pattern or the region of the area of the pattern in the input that the filter responds to. Right? So here are some examples from a paper very long ago. I think Krzyzewski's paper. This was a network that was trained to detect different kinds of objects. And if you go to the second layer and third layer filters and so on, the specific patterns in the input that make it respond are very specific to the input. But the first layer filters, they just respond to fixed patterns. And so here's what they found, that the first layer filters all ended up having patterns such as these. Are these familiar? Huber and Wiesel. I forget the names, right? But the 2 German guys, right, who tortured cats, they found that the human eye, the mammalian eye, responds to oriented lines. It turns out the CNN does so as well, which is beautiful, right? Then secondly, when inputs of faces were given, intermediate layer neurons ended up responding to parts of faces. Higher layer neurons ended up responding to entire face-like images. Where the input was a car, the intermediate layer neurons ended up responding to parts of cars. Higher layer neurons ended up responding to car-like images. And so also for elephants. You can see how as you go up, it's actually detecting, these things are detecting the receptive fields respond to more and more complex organizations of the input. Same thing with chairs. Now, there was another, we'll get to that. Training issues, you have standard convergence issues. So you need all the usual tricks of the trade, atom, momentum, what have you. And the number of parameters in your network can quickly become very large, even though you're sharing parameters. So you have to use tricks like data augmentation, where you basically take the original data, you can add noise, you can flip it around. If I place a bottle on its side, it's not going to not become a bottle, right? And so data augmentation essentially distorts the inputs in various ways to give you new training samples, and so on. So they are the most frequently used formalism today. They're used everywhere, not just in images. They're used in text. They're used in sound, you name it. Extremely popular, right? So there's some very nice examples of how they work on Karpathy's very old web page, which I recommend. Now, just spend a few minutes going on through the history of how all of this evolved. This is the last lecture on CNNs. CNNs, as they currently are, were proposed back in the 80s, in the late 80s. And they have been around for the longest time. And yet, neither they nor neural networks became particularly popular till recently, till about 2012. So this was the CNN that Jan LeCun had back in 1989 for detecting handwritten digits for the post office. That was the MNIST database. This was LANET 5, some details of LANET 5 there on the slides, right? And there it stayed till about 2012 because we weren't making any real progress. Then there was this remarkable paper on the ImageNet task by Jeff Hinton and co. So the ImageNet task is this large-scale visual recognition challenge data set, which has millions of images and about several thousand categories. 1.2 million images and 1,000 categories is a standard data set. And you're supposed to recognize images as the category that each input image belongs to. And before people began using neural networks, the best performance anybody got was like 25% accuracy. 1 in 4 was right. So then 25% error. It was pretty bad, regardless. And then there was this AlexNet, which came out in 2012. And this picture here is not like this because I cut it off. It's because this is how it appeared in the paper. Back in the day, the hardware was so weak that they actually had to split this network over 2 graphics cards. And so they drew the network, and when they split the network over 2 graphics cards, even the picture they drew became too large for the paper, so they chopped off the upper half. Right? But it had 60 million parameters, some 650,000 neurons, 5 convolution layers, pooling layers. This was the first time they actually introduced ReLU as an activation for convolutional neural networks. Before that, everybody was always using the sigmoid. And a whole bunch of details on the paper. They also added this additional trick where when they were, this is something you could use in your homework, where when they were classifying any image, they actually cropped it in many different ways, and they classified each crop independently and then took a vote. And so that gives you a nice performance, right? Performance improvement. And the error rate, which used to be 25%, went straight from 25 to 18.2%, the top 5 error rate. And if they used 7 such networks and used an ensemble of 7 networks, that error rate went down to 15.4%. And this is where the real research on neural networks took off. This was the paper that started the whole thing. And they also found this very interesting thing. Again, they find that the features that it learns at the lowest level look like what Huber and Wiesel said they would look like. And they found something more interesting. If you look at the final features that the network learns just before the classification layer, it ends up being very representative of the class. You could actually use it to perform retrieval. So here these are some standard examples. You can see that even when it makes mistakes, it's not so bad. This is a Madagascar cat. It's being recognized as a squirrel monkey. They're very similar. This is supposed to be a picture of a cherry, but it recognized it as a Dalmatian, and I don't blame it. Right? So anyway, but this is the interesting one. So this first case, this first column, represents pictures from which the final layer's features were extracted. And then based on similarity to the features similarly derived from other images, they selected the top several images as a retrieval problem. And you can see that for the flower image, it ends up retrieving other flowers. For the elephant, it ends up retrieving other elephants. So the final layer feature actually ends up being semantically relevant, which was a big thing, which is why in homework 2, you're going to use the final layer representation of your face recognizer to perform face verification, to retrieve things, new faces that you've never seen before. You can see why this works, right? And then, of course, there was an explosion in research. These guys, Zeiler and Fergus, they twiddled around with the AlexNet, and the error rate went down from 15.4% to 14.8%. Then these guys came up with, they burned down half the Amazon running experiments, and finally came up with a network with 140 million parameters, which was considered enormous in those days. These days, this is what you train for, homework 0, right? But that error went down to 7.3%. Now remember that just 2 years earlier, the error was 25%. Then Google likes to do, they like to make things complicated because, they want to show they're superior to you. You don't have the compute for it. So, and so they brought the error down to 6.7%. And then these guys, ResNet, came up shortly thereafter, 2015. And they just figured out how to pass derivatives through the network and made these networks really deep. And the error was down to 3.5%. Now, this is over 3 years. It's gone from 25% to 3.5%. And I want take a pause and imagine how that's been progressing, right? Some details about ResNet. Then there were other networks, and people came up with DenseNet. This became some kind of a cottage industry. Between morning and night, the error rate would go down a little bit. And papers would appear in archive left, right, and center. But anyways, the point is that the CNNs are now passé, right? We figured them out, or so we think. And they are used in places where you wouldn't expect them to be used. The last place I would have expected CNNs to be used was to analyze text. And again, they are part of the toolkit if you're processing text. For speech, where do CNNs come into speech? They're used for speech. A whole lot of other things. I'll stop right here. This was the CNN for speech recognition. This was another major improvement where they applied CNNs for speech, and they found that they could bring errors down to where it had never been before. And now this is all happened. So we'll stop here. Next week, we will either start with recurrent neural networks, or I am told by Ashwin that we might have a special guest who wants to do a series of 2 lectures. If that is the case, then we'll have those 2 lectures. But those will be on Zoom because he's not going to come here. They had learned.